This exam question is on the photoelectric effect from Unit 2. The first thing they want us to do is to work out or define the work function of a metal. So that's the minimum energy needed to release electrons. Okay, if you're unsure about that one, look at the keyword definition in some of the supporting paperwork. Next up, they want us to discuss how changing the intensity of light will affect the kinetic energy and the rate of ejection of electrons from a material. So the first thing I said when I answered this was rate will increase, and that's because there are more photons per second, but there'll be no increase in kinetic energy of the electrons because the energy is equal to E equals HF, and that remains unchanged by changing the intensity. So the next thing they want us to do is to determine whether or not we'd get the same emission if we had a different frequency of light. So we're going to have to do a couple of questions or a couple of things to get through this. It's worth 4 marks though, so it's worth investing a little bit of time on. So the first thing I did was work out what the work function of the metal was. So I did that the energy of a photon, so in this question here, the energy of these photons with frequency 7.4 must be equal to h times f. H is Planck's constant, which is 6.63 times 10 to the minus 34. And we're going to times that by the frequency from up there, which is 7.4 times 10 to the 14. And that is equal to 4.9 times 10 to the minus 19 joules. Now I'm confident because I always usually get photon energies to be to the minus 19 joules. Now the work function is equal to the energy of the photon minus the kinetic energy that went away. So that's going to give me 4.9 times 10 to the minus 19 minus the kinetic energy from up here, which is 1.2 times 10 to the minus 19, and that's going to solve to give me 3.7 times 10 to the minus 19. Now, I've not noticed, or you might have noticed, that I've not actually answered the question yet. I now need to find out how much energy is going to be provided by light of this frequency. So let's have a go. So we'll do E equals HF again. So that's 6.63 times 10 to the minus 34 times 5.1 times 10 to the 14 this time. And that's going to be equal to 3.4 times 10 to the minus 19. Now, you might have spotted this already, that 3.4 10 to the minus 19 is less than the work function. So, no emission. Very standard question, this one. Comes up lots of times, and I quite like it. Okay, so it gets a little bit messy on the next side, but if you work it through and if you're sensible, you can get there. So it wants us to derive an equation using some quantities that we might not be particularly familiar with. But if we start from somewhere that we do know, we should be able to get somewhere near their answer. So the first thing I did is start with my standard one, which is E equals HF. And I decided that I was also going to need the wave equation, which is C equals F lambda. C, of course, being the velocity of light, and therefore I said that the energy of a photon is equal to Planck's constant times C over the wavelength. Okay, so a bit of a rearrangement of this combined with this one here. And then I said that energy is equal to power times time, therefore the number of electrons I have times their energy, so this is the number per second, will equal power. And then if I take this from up here, so power is equal to the number of photons times Planck's constant, c, all over wavelength. Okay. Now it does say in the question that it wants it in terms of n, so a little bit of a rearrange will give me that n equals, so the lambda goes up, p lambda, hc goes down over hc. Okay. Just being confident and being familiar with what's going on. The fact that this is that power is per second and that n is also in per second is quite nice because those two ones cancel out. Then it wants me to derive an equation for momentum. So what I did here was I went for change in momentum is equal to the Planck's constant divided by wavelength. So that's another of the key equations. It's on your data sheet. And if I use my new equation from up here, which is n equals p lambda over hc, you may notice that h and lambda are turning up again in this. So we can do a bit of rearrangement, and that leaves me with P equals NC change in momentum, or P over N is equal to the change in momentum. I'm not really sure how the exam board wants me to express this one, so I've given it in a couple of ways in the hope that I've ticked their boxes. A student suggests that the answer to part 2 gives the pressure. Now, I'm not really sure about that because changes in momentum are equal to force times time. So I think instead of pressure, this young lady means, I don't know why it's female, means force. Okay, I hope that's helped. This question, quite tricky, involves you being able to play around with terms and equations and things. This one is just, can you spot what's going on with your wider understanding of physics? I hope that's helped. Goodbye for now.